Okay, so let's start on the second part of this lecture about visual illusions. I believe that at the end of this lecture, you're going to have a better idea about the reasons why we have to start with the human visual system. Because we see illusions. Not everything that we see is illusion, but our brain, the way our brain interprets the visual world, creates a number of illusions. One of them, that's a typical illusion that we see it's called the Mach band effect. You see that if you look closely at the limiting points between these sections of distinct shades of gray, you can see that it appears to be concave, but the actual intensity is constant. So that's one shade of gray in this portion up to here, another one up to here. There is no three-dimensionality. But the perceived intensity, we see that the borders, don't you see that this sort of goes up? I see better this effect here and here, right? Let me change the pointer option. Maybe you'll see better. It goes up and down here, as if it were a folded paper. Why is that? That's because, well, that's evolutionary, of course, but that's a way of our brain to reducing the complexity of the visual world by judging three-dimensional features where from two-dimensional figures. I'm not sure if you've heard before or parts of it. We have two eyes. Why we have two eyes? Because this gives us a stereo vision. This gives us a notion of depth. But the depth that we get, the depth perception that we get with two eyes goes up till the longest strength of my arm. So it goes up till here. Beyond that, we don't use stereo vision for judging depth. We use other cues. This is one of them, the Mach band effect. Of course, if you see in this way, it appears to be well, useless, but actually we use it to infer three-dimensional features on our bidimensional images that we see of our external world beyond the reaches of our arms. Another related issue is this notion of simultaneous contrasts. We've seen in the previous part of this lecture that our eyes adapt to the context. It adapts to the surroundings. You can clearly see, well, maybe you can't. I definitely see that this middle square here is lighter than this square here. But if you do this experiment at home, print this light, cut the middle piece here, cut the middle piece there, and cut the middle piece here, you're going to see that these three are the same. These three have the same shade of gray. It's just that when we look at this one, as the surrounding, as the context is darker, we interpret this gray box here as lighter, whereas here, as the surrounding is brighter, we tend to identify this middle square as darker, but this has the same shade of gray as this, and this has the same shade of gray as this other one. Right. This is even more evident on this experiment. Instead of explaining, I'll show you this YouTube video where this is quite amazing. So bear with me for a second. Here we go. You don't believe me? Try it yourself at home. It's quite amazing. And why should we bother about it? Well, your computer vision system, your image processing system is going to see this this square as exactly the same shade as this square. And then you're not going to understand why you can't segment this square in the same way that you're segmenting this square, because you know for you as a human, this has exactly the same intensity as this square here, whereas it has not. It has the same intensity as these square, and these, right? So and then you're going to think that your system is broken, that computer vision doesn't work, that it's no, that's your eye that's mocking. And you have to take that into account when you're developing an algorithm for a client, when you're developing an algorithm for a robot, and you want to understand why your robot doesn't work the way that it's supposed to, given how you perceive the world, how you, informally you understand your external world. This is another good one. I'll show you this video. That's another ball game, but it's kind of related. It's the way we interpret shadows, and we use depth cues to interpret shadows. Now tell me what you saw. Did you see movement in the image? Let's see again. Pay attention to the green square in the middle. It seemed that it moved up, right? It seemed that it moved up, but it didn't. Now, do the following. Cover this part of the square with your hand and watch the video again. Do it now. Cover this part of the square. Don't see, but basically you are occluding the shadow. And just look, or if you are far away from the screen, or I don't know, you're doing something else, just look at this corner and ignore this corner of the square. It's better really if you put a piece of paper on top of this part. Let me do it again. The square doesn't move at all, but the movement, the object doesn't move at all, but its shadow, depicted shadow, moves. It enlarges, so it gives us gives us the impression that the object is coming up towards the viewer. That is the way we interpret the visual world. We use these depth cues to understand 3D, to understand the 3D world. We don't have three-dimensional vision. We have three-dimensional vision up to the end of our arms. That is the radius around which we have three-dimensional vision. Beyond that, we mostly use depth cues such as shadow movement. I'll play that again. That's quite amazing. Sorry if I'm bothering you, but it never gets old. The square doesn't move at all. Let's see another example of the same thing. Watch it and tell me, oh, that's in the other slide, sorry, my fault. Let's go, that's the one. Tell me what happens with this sphere, with the little ball in a box. So it seemed that on the first movement, the sphere moved in depth, right? It moved in this diagonal. And in second time, the sphere seems to be to have moved in this direction, but going up above this checkered board. Let's see again. Did you see the apparent motion? Now, if you haven't seen it, now cover the shadow. Put your hand or a piece of paper under this part of the screen and watch again. The sphere executes the exact same motion in both times. So it just moves from here to here on the screen. You see that this is a bidimensional depiction, and it doesn't have three-dimensionality, but we are judging. It seems that in one time the sphere moved in depth, in the other time it just moved horizontally, but going up above towards this part of the screen. Again, that's how our brain interprets the world. And that's the some of the variables that we have to take into account when we're analyzing the results, when we're developing our algorithms, and we're analyzing the behavior of these algorithms. Now, if you want to know more about shadows and depth perception, you are very welcome to download my papers. Well, there's a few of them, and this one is a good one. That's an interdisciplinary review. It talks about various fields that take shadows into account, from computer vision to cognitive sciences. This is an extension of that work. That's the introduction of a special issue that I organized with a few colleagues. And this is the application of these ideas on a mobile robot environment, with a mobile robot navigating in an office-like environment. Okay, so there are other illusions that we have to take into account. I'm sure you've seen pictures of this in the internet. So you know that there is no square here. You're just seeing this square because you're identifying, your brain is trying to find a pattern using these circles with a hole in it. So there is no square here. And now imagine yourself trying to develop a computer vision system that would segment this square. It will never segment any square here because there is no square here, right? The same here. I clearly see a circle, but there is no circle here. This is a fun one. So you see, if you can you see that one? Can you see that one line segment seems to be longer than the other? So this seems to be a longer line segment than this one. But if you again put your hands, cover these the terminal points, the terminal features, and you're going to see that they are exactly the same size, the same length. And this one, there's no way that these line segments are parallel, but they are parallel. So this is a parallel to this, that's a parallel line to this, and that's a parallel line to that. So why I'm seeing that they are converging. So this one is converging to that, and this one is like diverging to the other. This is diverging to this. We don't see them as parallel. Again, that's this is our brain trying to interpret a two-dimensional picture as a three-dimensional scene. Let's move on. So this is a good one. Can you count the black dots here? I'll give you a few seconds. Try to count how many black dots are there in this picture. You can't, right? Why you can't? Because there is no black dot. There is not a single one. It's not that's moving. It's not like an animated GIF. It's not a film. That's a static picture. Now, this is an effect called center surround perception, centers around perception. We've seen in the previous lecture, in the previous part of this lecture, that you have the receptive fields of, you have your ganglion cells, and each ganglion cell is connected to a receptor or a bunch of receptors. And what happens here is that given the context here, as we are trying to make sense of the color in the middle, given the context, what's going on is that, well, this is a very waving hand way of explaining it, is that there is an overlap between the perception of one bunch of receptors and another bunch of receptors. So while one group of receptors is seeing this, taking into account the context or the surrounding, the other cells are trying to see this. So we are actually seeing both. We are seeing a black dot and a white dot at the same time on this. Even though there is no black dots. Right, again, can a computer vision system see that? Well, if you develop a computer system that's human-like, it might, but it doesn't exist. It doesn't exist. So yeah, the computer systems, the computer algorithms that we have, they run they are implemented in a programming language such as C or Python, and they're basically algorithms, not much different from any algorithm that you've developed in your life or in previous topics that you've done here. Okay, again, why should you be bothered about it? Just to conclude, any work on image processing, the end user is a human, right? So you're developing an image processing algorithms for analyzing medical images, but who's going to use the results of your image processing algorithm? Is a medical doctor, is a human. So you have to take into account the human perception, how your client is going to see the results of your computer vision algorithm. So that's why you should be aware about what and how we as humans see the world. And your algorithm, the development, I should have said, the development of your algorithm should take that into account. And if you, on the other hand, you are working on computer vision or robot vision, it's the same as above, but the final client is not usually a human. The final client is a robot, is a machine, is a mechatronic system, is an intelligent system. But you have to understand when it doesn't work, it may not be that your algorithm is incorrect. It may be that your interpretation of the world is different from the interpretation that you're getting from your computer vision algorithm. If you want to learn more about all of this, there's this wonderful tutorial. This was presented in the CVPR. That's a computer vision and pattern recognition conference. That's one of the best conference of computer vision in the world. And there's a bunch of slides on this site. It's a crash course on human vision. It's excellent. Unfortunately, I didn't have time to see it all, but what I've seen is just unbelievably good. Some of these slides were inspired by talks given at this tutorial. And obviously, this is part of our book. This is section 2.2. I'll see you in section 2.3 in a minute.